second unit, that is in the same subject, that is pharmaceutical in organic chemistry. So we are going to start our unit number 2. The name of the topic is acid, bases and buffers. Basically, in the case of unit number 2, there are 3 chapters. Chapter number 1 is acid, bases, buffer. Second 2.2 is major intra and extracellular electrolytes, and bit number 2.3 is dental products. So we'll discuss about acid, bases and buffers. Already we have seen the now what content we are going to cover in this topic. We are going to cover definitions of all, that is acid, base and buffer. Then we are going to cover types of acids, types of bases and types of buffers, their uses in the pharmaceutical important point of view, different theories behind acid, bases and buffers, some of the examples and references we are going to cover. Now uh, we are moving towards the definition of acids and bases. Already we have discussed in very first lecture these definitions, just we will revise them according to now Arrhenius, then Laurie Bronsted, then Lewis has proposed their own different definitions of acids and bases. So according to Arrhenius, what is acid basically? So according to Arrhenius, acid is a substance which will produce H plus ion when it is dissolved in water as a solvent. So if any compound, if it is dissolved in the aqueous solvent, if it is going to donate H plus ion, then that compound is referred as, that compound is known as acid substance. If any compound in water media, if it is going to produce H plus OH minus ion after dissociation, so those are all compounds coming under the category of bases. So according to Arrhenius, acid is producing H plus ion and base is producing OH minus ion. Now the limitation of as Arrhenius theory, that this theory is only work out in the presence of water as a solvent. It will not work out in the presence of organic solvent, and if the solvent is not there. Some of the reactions are there that are carried out in absence of solvent also. That time we cannot judge which compound is acidic in nature and which compound is basic in nature. So this is the own limitation of this Arrhenius theory. It will not explain the compounds behavior, whether it is acidic or basic, in the absence of water as a medium. So later on, Laurie Bronsted come forward and he put forth his own definitions, his own concepts of acid and bases. Now, particularly this Laurie Bronsted theory work in a presence of any solvent. So there is no any limitation that presence of water must be there or presence of aqueous solvent must be there. This type of theory will work out in the presence of any solvent. So according to Laurie Bronsted, what are acids? Acid is a compound which will donate H plus ion. The compound during reaction, during equilibrium, if any compound is going to donate H plus ion, that H plus donor compound is known as acid, and a base, the any compound which is will be accepting that H plus ion which is donated by that acid compound is known as base. Now this particular concept is working in the presence of any solvent. There is no any limitation for the presence of water as a solvent. So this is and having his own application as well as limitation, that this theory requires presence of solvent in it. Any type of solvent we can say, but it requires the presence of solvent media to produce or donate H plus ions and accept H plus ions. So this is according to Laurie Bronsted theory. Now, third and very important concept, and which we are now using nowadays also, this is having quite less limitations, broadly classified into Lewis acids and Lewis bases. So this terminology, that is Lewis acid and Lewis base, used in the briefly in the organic chemistry, and this theory, or that is Lewis theory, is going to cover wide range of the substances in the acidic and bases. Many of the organic compounds is also covered in this Lewis concept of acid and base. So according to Lewis, what are acids? A compound which are going to accept a lone pair of electrons. So this concept is totally depending upon the donor and acceptance theory of the electrons. So according to acid, a compound which is going to accept a pair of electrons is known as acid, and a compound which will donate a pair of electrons is known as base. So according to Lewis, this is an exchange of electrons theory. So many of the organic compounds are covered in this category of Lewis acids and bases. So we will just discuss some of the examples of acids and bases according to different proposals of Arrhenius, Laurie Bronsted and Lewis. Now, the examples of acid and base according to Arrhenius is, Arrhenius acid is hydrochloric acid and Arrhenius base is sodium hydroxide. Arrhenius is going to produce H plus ion and NaOH is going to produce OH minus ion. So according to Arrhenius, HCl is acid and NaOH is a base. Then according to Laurie Bronsted, H plus donor is acid and H plus acceptor is base. Now here hydrochloric acid is H plus donor, but HCl and NH3 they are, sorry, NH3 is a hydrogen acceptor. So NH3 is a base. Now according to Lewis acids and base, so BF3 can be categorized as a electron acceptor. He is going to accept the electrons. So BF3, boron trifluoride is coming under the category of acid, and ammonia, as like that of Laurie Bronsted theory, it is coming under the category of base. Now what is the meaning of the word neutralization concept? How this neutralization will happen? Now the result of this neutralization theory, neutralization reaction is formation of salt and water. What is neutralization? Whenever there is reaction between any acid and a base, if they are reacting with each other, so they will result into formation of salt and water. So this is a normal concept, widely used, universal concept. Whenever there is a reaction between acid and a base, it will result into a formation of salt and water. See, all the neutralizations reactions are double displacement reaction. Now, why these all neutralization reactions are known as double displacement reaction? Because a displacement of H plus ion is also happening and a displacement of OH minus ion is also happening during the formation of salt and water. See here, H plus will be displaced from hydrochloric acid to the water molecule, and NaOH, Na plus ion is displaced from NaOH to the Cl minus. So both of them are, both the reactant are displaced from their place. That's why all the neutralization reactions are known as double displacement reaction. Now take a screenshot of this slide. You are going to complete these two reactions, a reaction between hydrochloric acid and magnesium hydroxide, and a reaction between sulfuric acid and sodium bicarbonate, as like that of above reaction. You are going to complete this reaction. This is just and for understanding purpose. Take a screenshot of this and you are going to complete this reaction. Now, some of the examples of strong and weak acids and strong and weak bases. Now, what is the meaning of the word strong acid, strong base, weak acid, weak base? Now, the definitions of strong acid and strong base are any substance, whether it is acidic or basic, if it is 100% dissociated in the solvent, then it is known as a strong acid or a base. Whether it is acid or a base, forget about that. If that compound is completely ionized and dissociated in the compound, then it is known as strong acid and a strong base. So here the mineral acids, hydrochloric acid, nitric acid and sulfuric acid all are completely dissociated in the uh, all are completely, that is 100% dissociated into their respective ions. So they are coming under the category of strong acids, and potassium hydroxide and sodium hydroxide are coming under the category of strong base. Whereas a compound, weak acid and a weak base, they are not totally dissociated into their respective ions. There is a partial dissociation of both the ions in the molecules. So the compounds which are not 100% dissociated, they are partially dissociated into their respective ions. Those compounds are known as weak acids and a weak base. So according to a theory of weak acid and a weak base, acetic acid is coming under the category of weak acid and ammonia is coming under the category of weak base. Now this a slide is in front of you, will give us some of the examples of acidic compound and basic compound. So boric acid, hydrochloric acid, nitric acid, phosphoric acid, sulfuric acid are all are coming under the category of acidic compounds, and ammonia, potassium hydroxide, sodium hydroxide, soda lime are coming under the category of basic compounds. Now, before we move towards a very important point, that is buffer solution, we will discuss the theory behind that. Now, the equilibrium between the weak acid and its conjugate base. Now, what is the meaning of the word weak acid? Weak acid is nothing but it is not completely dissociated. It is partially dissociated into its ion. So, this partially dissociated conjugate, partially dissociated weak acid and its conjugate base allows the solution to resist the change in the pH value. So that's the a mixture of solution of weak acid and its conjugate base will resist the change in the pH value when when we are going to add a small amount of strong acid or a base. The presence of weak acid and its conjugate base will not allow the solution to change its pH value. This phenomenon of resistance of change in the pH value is known as buffer solution. So the buffer pH can be estimated using a very important equation, and that is known as Henderson-Hasselbalch equation. Which equation is known as Henderson-Hasselbalch equation? It is pH is equal to pKa plus log of concentration of A minus ions divided by a concentration of HA ions. Here the A minus ion denote the molar concentration of conjugate base of the acid, and HA denote the molar concentration of weak acid. So here this A belongs to conjugate base of that acid and HA belongs to concentration of that acid itself. So the ratio and logarithmic pH is equal to pKa plus logarithmic ratio of concentration of conjugate base divided by acidic concentration is known as Henderson-Hasselbalch equation. Now, what is this equation actually? The Henderson-Hasselbalch equation provides a relationship between a pH of the acid in the aqueous media and their pKa. What is pKa? pKa is the value of any dissociation constant of that acid. So the ratio of H plus ion and their dissociation constant value is known as Henderson-Hasselbalch equation. The pH of the buffer solution can be estimated with the help of this equation. If we don't know the pH of any solution, with the help of this equation, we can calculate the pH of this solution. And the Henderson-Hasselbalch equation can be written as pH is equal to pKa plus log to the base 10 a concentration of A minus ion, whereas where the A minus ion is basically, what is A minus ion? A concentration of A minus ion denote the molar concentration of conjugate base of that acid, and HA is belongs to the concentration of that weak acid itself. So therefore, the Henderson-Hasselbalch equation can be written as pH is equal to pKa plus log a conjugate base. That means if we are going to take a mixture of acetic acid and sodium hydroxide, or acetic acid and ammonia, so there is a reaction will happen, as there is a reaction between the acid and ammonia, acetic acid and ammonia. There is formation of water and salt solution, that is ammonium acetate. So this ammonium acetate is the conjugate base of that acetic acid. So the ratio of conjugate base to the acid is known as Henderson-Hasselbalch equation. An equation that could calculate the pH value. By using this Henderson-Hasselbalch equation, we can calculate the pH value of the buffer solution. Was first derived by this phenomenon of calculation of pH value, which is first derived by the chemist, that is Henderson. This phenomenon is actually first derived by the American chemist, that is Henderson, and this equation was then re-expressed in the logarithmic form by the scientist Hasselbalch. So combinedly, the result of this equation was known as Henderson-Hasselbalch equation. Now, the derivation of this Henderson-Hasselbalch equation is nothing but, so this is a derivation of this Henderson-Hasselbalch equation. Let us take an example of ionization of weak acid HA. So here we have taken a weak acid HA.
चालू झालंय त्याला हे आता चालू झाले ना हे त्याला हजेरी लावायला लागते शेवटला आपला नंबर टाकायला लागतो
So let us take an example of ionization of weak acid HA. So this weak acid HA, when it is dissolved in a water molecule, so this HA, when it is dissolved in water molecule, so it will partially dissociated into its ions, H plus ion and A minus ions. Now, acid dissociation constant, that is Ka, can be written as, it is nothing but the concentration of H plus ion multiplied by concentration of A minus ion, that is dissociated ions, divided by the concentration of HA, which we have taken for the reaction mixture. Now we are going to take the negative logarithms of all these. So minus log of Ka, minus log of H plus A minus and HA. So we are going to simplify the equation. The equation above can also be written in the form of pKa is equal to pH minus log of concentration of A minus multiplied by concentration of HA. So if we are going to rearrange the equation, now here in the case pKa is in the left hand side of the equation and pH is in the right hand side of the equation. If we can rearrange this equation, so for the calculation of pH value, pH is equal to pKa plus log of concentration of A minus and concentration of